Although ostensibly a rotational speed measurement, rotational speed sensors can be employed with very little modifications to perform measurement of other physical phenomena, examples being fluid velocity and flow rate. Consider an anemometer, a means of measuring wind speed or fluid velocity. An anemometer is essentially a rotational speed sensor. As wind speed increases, the anemometer registers more revolutions per sample window and outputs a voltage signal proportional to wind speed. Wind speed is critical information for weather stations and the efficient and safe performance of modern horizontal axis wind turbine generators. Alternatively, consider one type of flow meter, which immerses a paddle wheel or turbine blades in a liquid or gas. If rotational speed is proportional to fluid velocity, the flow rate, a measure of volume per unit time, can be calculated using the cross-sectional area of the pipe through which the fluid flows. Like I said previously, the transduction process is often a game of telephone, where one quantity must undergo a series of complicated transactions before it ultimately outputs a voltage or current signal proportional to the measured quantity. It goes without stating there is often some complicated math, a degree of computation, and demanding electronics knowledge that goes into the design and construction of a sensor that I am purposely overlooking in the interest of brevity. Moving on, let's examine representative examples of position sensors. Simple position sensors can be best conceptualized as a potentiometer and a voltage divider arrangement, where displacement affects the observed voltage at the central terminal. Consider a 10 kilo-ohm potentiometer with a 10-volt differential across the A to C terminal. When the central B terminal is adjusted to 75%, such that 2.5 kilo-ohms of the available 10K appears between A to B terminals, and the remaining 7.5K appears between the B to C terminals, it can be quickly demonstrated using the voltage divider rule that the voltage drop across the A to B terminals would be 2.5 volts, and the voltage drop across the B to C terminals would be the remaining 7.5 volts. If the central terminal is displaced midway, it can again be demonstrated using the voltage divider rule that the voltage drop across the A to B terminals would be 5 volts, and the voltage drop across the B to C terminals would be the remaining 5 volts. For those requiring assistance with the voltage divider rule, please check out the DC voltage divider rule lecture available at the Big Bad Tech channel. Ultimately, as the position of the potentiometer central terminal is physically varied, so would the voltage output. The potentiometer output has in effect become a sliding scale representative of linear displacement. As primitive and crude as this method seems, it's effective. Consider a potentiometer with a rotational adjustment knob to which is attached a spring-loaded coil of wire. If the wire is attached to the tip of a hydraulic cylinder rod, as the rod extends, it unwinds the cable and rotates the potentiometer adjustment knob. Conversely, when the rod retracts, the spring-loaded coil reels in, returning the potentiometer adjustment knob to the start position. Voltage at the output terminals would therefore be proportional to linear displacement. At commissioning, the zero in span of this potentiometer-based position sensor would need to be adjusted for full retraction and full extension. Assuming linearity, and let's say a cylinder with a 10-inch travel length just to keep the math easy, the 10-volt output range is broken into 1 volt per inch chunks. The problem with this contrivance is that it's riddled with inefficiency and mechanical problems. The wire could stretch over time, the reel could bind, or any number of tolerance issues could develop, all servicing to decrease the accuracy and response of this system. Significantly more sophisticated linear position sensors exist, including linear variable differential transformers, sometimes called linear variable differential transducers, both conveniently abbreviated LVDT, and magnetorestrictive waveguides. We briefly introduced the LVDT when we examined the proportional valve, where it was employed as a spool position sensor. However, we kind of shortcut the details. An LVDT consists of a magnetically permeable core that slides inside a hollow bore. Around the hollow bore are wrapped the windings of a primary and 2 secondary coils of a transformer. When the primary coil is excited by a high-frequency AC source, an output voltage is observed on the secondary coils via electromagnetic induction. Assuming a perfectly centered core, there would exist no differential between the two secondary transformers. However, if the core is displaced towards one end or another by an object to which it is mechanically coupled, whether this object is a tiny spool inside a proportional valve or the rod of a large hydraulic cylinder, there would exist a differential proportional to the core displacement. Signal conditioners internal to the LVDT would format the differential as an analog representation of linear displacement. Another common method of linear position measurement makes use of a magnetorestrictive waveguide. Using this extremely cunning method, a position magnet is mechanically coupled to a linearly moving object, and this position magnet floats or slides along a waveguide. As the object moves left or right, the magnet comes along for the ride. Regular tiny pulses of current are sent down the waveguide. When the current pulse, itself carrying a radial magnetic field, reaches the position magnet, there is an interaction between the two magnetic fields that produces a torsional or twisting strain in the waveguide. The torsional strain pulse propagates the length of the waveguide at ultrasonic speed. At the receiver end, the pulse is converted to an electrical signal. Given the ultrasonic pulse is traveling at a regular and predictable speed, the time span between the generation of the current pulse and the receipt of the ultrasonic echo is a highly accurate representation of the linear displacement of the position magnet. Again, with subtle alterations in deployment, these methods of linear position transduction can be employed to measure other quantities. Consider a level sensor making use of a magnetorestrictive waveguide where float is coupled to the position magnet. As the level in the tank varies, the float slides the position magnet up and down the waveguide, and the sensor outputs an analog value proportional to the quantity of liquid in the tank. Another alternative application of a position transducer is that of vibration measurement. Consider an extremely minute yet incredibly precise position transducer, as whatever the vibration sensor is attached to, be it a gearbox, bearing, or frame, bounces up and down due to misalignment, lack of lubrication, or some other influencing factor, the vibration sensor measures this displacement. One last quick example of transducers, temperature sensors, before we move on to another topic. Several different types of temperature sensors exist, two of the most common being RTDs and thermocouples. RTD stands for Resistance Temperature Detector. The principle of RTD operation is positive temperature correlation, and that if you heat something up, its resistance increases. RTDs are often made of platinum because the proportional variation of resistance as a function of temperature is linear, precise, and repeatable. The RTD is in effect a thermistor, a resistor that varies as a function of temperature. Using the principle of Ohm's law, perhaps you've heard of it, observed voltage and current properties relay temperature variations. Thermocouples are another type of temperature sensor that operate on a totally different principle, that principle being the thermoelectric effect. A thermoelectric device generates a tiny yet predictable voltage proportional to the temperature differential across it. One end of a thermocouple, the reference or cold end, is maintained at a constant temperature, and the other end, the measuring or hot end, is exposed to the process being measured. Via the onboard signal conditioning electronics, a proportional voltage or current signal is generated representative of temperature. I feel like I could go on like this all day with more and more examples of physical phenomenon being represented via various transduction methods, but I've got to draw a line somewhere if we want to keep this lecture manageable and introductory in nature. Long story short, a sensor is not only a detection mechanism, but also a means of measuring a quantity. Via the transduction process, the physical phenomenon being measured, whether it is pressure, rotational speed, wind speed, flow rate, position, level, or temperature, is represented as a proportional voltage or current quantity. By adjusting the zero in span, an operational range can be established and appropriately scaled for the particular application. Left unasked until now is the very valid quandary. Why is this proportional representation of a measured quantity so important that I'm sitting here watching this lecture instead of playing with my dog? The answer is many-layered, and true appreciation of analog representation of both input and output will come in time. However, I can summarize its significance with a couple important applications, namely data recording and process control. A very simple and straightforward application of analog sensors is often the very real need to record data for the needs of some process or for the purposes of troubleshooting should a fault occur. Consider a modern horizontal axis wind turbine generator with numerous sensors relaying data to the control system. Rotational speed sensors measure the rotational speed of both the low-speed main shaft and the high-speed shaft. An anemometer measures wind speed. Temperature sensors measure the temperature of the gearbox and generator. Vibration sensors monitor vibrations of the gearbox. Angle transducers measure the pitch angle of the blades. Integrated current transformers and voltmeters measure input and output electrical quantities, and so on. On a continual basis, the control system records and stores this data relayed by the sensors. Additionally, this data can be transmitted to a remote supervisory control and data acquisition network. Should a fault occur, either an overcurrent event, excess vibration, or overspeed condition, the turbine control system can initiate a safe shutdown. Having access to all the data at the time of a shutdown, a technician, remote operator, or the automated system itself can make a decision to resume operation or initiate a call for service. Additionally, historic trends can be captured and analyzed using the accumulated data. For example, if the vibration sensor on the main shaft bearing indicates an increasing trend, a technician can be dispatched to perform inspection or preventative maintenance before the issue becomes a deal breaker. This type of predictive maintenance would not be possible without a sensor that not only detects a quantity, but also measures and quantifies it. I should note with delicious irony that the analog data relayed by sensors is stored and sometimes transmitted in a digital format, since computers kind of struggle with analog data. Computers find packages of digital data easier to transmit, store, process, and more resistant to electrical noise. A detailed understanding of digital to analog conversion and vice versa is not essential to our current level of understanding, but as an example, the analog value of 10 in base 10 number system can be represented using regular 8-bit binary or base 2 system as 00001010. Those interested in binary numbers are encouraged to check out my lectures on digital electronics. Regardless, analog to digital and digital to analog converters make this conversion process from one format to another a possibility. Another important application made possible with sensors is that of process control, the most basic aspect being that of comparison. The end goal of most systems is to produce some desired output, often called the process variable. This could be the exertion of a given amount of force over a certain distance, keeping the rotational speed of a shaft inside a given range, maintaining liquid level in a tank constant, holding or moving an actuator and applied load to a certain position, keeping the temperature in a room constant, or some other measurable result. This ideal result is known as the set point. Two general classes of controllers exist for such systems: open loop and closed loop control. An open loop control system is a means of process control that does not use feedback to determine if resultant output has achieved the desired goal. This means that the system acts upon but does not observe the resultant output of the process it is controlling. Consequently, while simple and relatively inexpensive, an open-loop control system cannot automatically correct any errors, nor can it compensate for disturbances. A closed-loop controller, in contrast, is one that does use sensor feedback to determine if resultant output has achieved the desired goal. This means that the system not only acts upon, but also observes the resultant output of the process it is controlling. Consequently, a closed-loop controller can compare the output process variable with the desired set point. If a differential between the output process variable and set point exists, an error in excess or detriment is registered, and the closed-loop control system can automatically correct any errors and compensate for disturbances. Keeping with our earlier wind turbine generator example, the generation process is most efficient inside a range of rotational speeds. Given wind is not a controllable quantity, a turbine does this by pitching or changing the angle of the blades, either spilling excess air or moving them towards a more aggressive attack angle. Assuming a set point of 1850 RPM at the high-speed shaft, a closed-loop controller can be used to maintain the high-speed shaft rotational speed close to this value despite variations in wind speed. Assuming the rotational speed sensor produces a 0 to 10 volt output linearly proportional to speed inside a 0 to 3600 RPM range, it can be demonstrated that the transfer function is approximately 2.8 millivolts per RPM, and that a value of 1850 RPM corresponds to approximately 5.1-ish volts. Assuming the high-speed shaft really is at 1850 RPM, both the set point and feedback are at 5.1 volts. And the differential, or error between them, is 0 volts. No error signal is sent to the controller, and no adjustment to the wind turbine is warranted because rotational speed is exactly where we want it. Let's say a strong gust of wind strikes the turbine, and the rotational speed of the high-speed shaft briefly increases to 1900 RPM. The feedback signal rises to approximately 5.3 volts, and there exists a differential of approximately negative 0.2 volts in excess of the desired set point. Note the polarity of the set point and feedback at the point of comparison, often called the summing junction. The set point is positive and the feedback is negative. When the feedback is in excess of the set point, the error is negative, meaning that the system actuators need to lay off the gas in an effort to reduce the output. Noticing not only the magnitude of the differential, but also the polarity, the controller can signal the blades to pitch back and spill some wind. Rotational speed drops and eventually stabilizes at 1850 RPM such that there exists no differential between the set point and feedback. Coming at this from the other end, let's say the turbine experiences a momentary lull and the rotational speed of the high-speed shaft decreases to 1800 RPM. The feedback signal drops to 5 volts and there exists a differential of approximately positive 0.1 volts. Again, accounting for polarity of the set point and feedback at the summing junction, the error is positive, meaning that the system actuators need to step on the gas in an effort to increase output. Noticing not only the magnitude of the differential, but also the polarity, the controller can signal the blades towards a more aggressive attack angle. Rotational speed increases and eventually stabilizes at 1850 RPM, such that there again exists no differential between the set point and feedback. By continually monitoring and comparing the process variable through sensor feedback with the set point and adjusting actuators to respond to changes positively or negatively, the closed-loop controller keeps the rotational speed inside this desired range and the generation process as productive and efficient as possible. I've obviously simplified this process, neglecting numerous influencing factors such as wind and yaw direction. However, the larger principles are pretty accurate. The larger take-home point of this lecture, focusing on an introduction to sensors, being that a closed-loop controller would not be possible without a sensor measuring the resultant output process variable. Sensors capable of producing continuously variant analog representations of the quantity being measured make this level of process control a workable reality. Alright, that's about it for our quick introduction to sensors. No, we did not cover everything, and I've made some obvious sweeping generalizations, but we did gain general knowledge of sensors and the transduction process, and at least a basic knowledge of how they are employed in a control system. As time and occasion allow, I hope to examine specific sensors and control systems in greater detail. Until then, this will serve as at least a general introduction. In conclusion, this lecture took a brief introductory look at sensors or transducers. We examined various methods of transduction for pressure, rotational speed, fluid velocity, flow rate, position, level, vibration, and temperature. Additionally, we discussed transfer functions and the process of adjusting the zero and span of a particular sensor. Finally, we examined how sensors are employed in closed-loop controllers and how closed-loop controllers can automatically correct any errors and compensate for disturbances. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.